fundamental apprehensions about CFD. So in my presentation, I have included only one set of equation, and I will be explaining that in a very lighter way. And whatever doubts you are having, you can type in that to the group chat. I will try to address all that at the end of the session. Now, coming into definition of a fluid, to the classical definition, it basically means that anything that can flow, we can include that as a fluid. But going on into a higher way, a fluid can be defined as any substance that can deform continuously when a shear stress acts upon that. So we know what stress is. Stress is basically defined as the internal resistance divided by fluid area. And shear stress, as you can see in the presentation, a shear stress is something that acts upon tangential of a body. So if you are having a tangential force acts on a body, it tends that force, it tends that object to deform in a particular way. If it is a solid, the developed deformation will be much lower compared to the amount of stress that is, or compared to the amount of force that is acted upon that. Similarly, if you are having a water or any other fluid like this, very minimum amount of force acted upon that will actually tends to generate a large deformation on that body, whether that be liquid or whether that be gas. As the molecules are not tightly packed as that of a solid object, that force will tend to generate a large amount of deformation. And this deformation is of very much important to us, as fluid flow constitutes many of the engineering problems around us. Not just engineering problems, starting from our human body, the movement of air around us, the rotation of Earth, the revolution of Earth, the movement of waves, all these constitutes basically fluid flow only. So in order to define a fluid, we certainly need a certain type of properties that is basically defined as the basic address of that fluid. So coming into fluid properties, what constitutes the addresses are basically viscosity, density, pressure, temperature, velocity, in such a way that each of these have a certain role in defining how this fluid flow will behave. Coming to viscosity, as most of you might be knowing, viscosity is the resistance offered to the flow in layers. You have density, mass by volume. So all this actually defines how the fluid will behave or how the fluid will be constituting a particular area. Going on to our next aspect. So, as I have stated, almost many of the engineering problems around us constituting a fluid flow, we need to analyze how this fluid will behave in a certain way. So in order to analyze how the fluid will be moving or how the fluid will be behaving, there are three steps or there are three areas or thrust areas where we can identify how the fluid will be behaving and how the fluid will be operating in a particular way. For that, we have three aspects. First one is fluid statistics, second one is fluid kinematics, and third one is fluid dynamics. Coming into fluid statistics, it means that the fluid will be held stationary and you carry out the analysis based on that steady state, or not the steady state, that state in which it is at rest. Then you have fluid kinematics, in which there will be a minimal displacement provided to the fluid without the application of force. And at the last, we have what it is termed as fluid dynamics, as the word dynamics moving. It actually institutes a force that is acted upon that fluid, and by the effect of that external force, or whether being an internal one, how the fluid will behave in certain way. That is our basic understanding of fluid dynamics is all about. If it constitutes an internal force or whether it constitutes an external force, how the fluid will behave, that actually consisting of the fluid dynamics aspect. Coming into computational fluid dynamics, we'll be making use of some computational power to carry out that fluid dynamic analysis. That is all about fluid analysis as well as computational fluid dynamics, as a brief introduction is about. Fluid dynamics. And you can iconically identify these two persons. There is no doubt in that. The first one is Sir Isaac Newton, and to my right side, to the right side of the presentation, we have Sir Albert Einstein. So these two people have actually constituted the entire engineering analysis systems in the world. Whatever physical phenomena you take, whatever physical phenomena we are attempting to analyze, that will be governed by the laws that are governed, or the laws that are generated by these two stalwarts in science. Engineering is basically the younger brother of science. Engineers, what basically does is that we make use of the laws in a practical way. And coming to fluid dynamics, the most major or the most important contributions are made by Sir Isaac Newton. And as Einstein has said, he generated principles onto how we can apply those principles in an actual practical way. So this is the basic contributions made by these two stalwarts to the area of fluid dynamics. And the fundamental understanding of fluid dynamics starts with this basic law, that is Newton's second law. It states that, suppose over here you have an object or you have a body that is kept in the state rest at the 0 time. That means it will be having very less velocity, or let be having a velocity v0, with having a mass t0 at a position x0 at the time t0, and an external force act upon this body, and it tends to displace the object to a new position in such a way that its mass changes, volume changes, time changes, as well as position changes. This mass change may not be there always, but in actual conditions, or if you are taking into a microscopic conditions, there will be mass change. So what actually constitutes this acceleration is the change of velocity with respect to time, or we call that as the velocity gradient in terms of the position as well as the velocity. That terms the acceleration over here, and the total force generated on that object would be the mass into acceleration. This is the fundamental governing principle of fluid dynamics. Whether that force being an external one or an internal one, the magnitude of the force will be equal to mass times the acceleration generated. So working on this, in the initial times, people started analyzing fluids, how they tend to behave when a certain amount of force is being acted upon them. However, that were just basic understanding that this equation could hold value. So what happened over time was that the theoretical analysis developed were not suitable to address the actual physical phenomena that were happening around us. So in that condition, initially the first equation of E is equal to ma, there you can convert that equation into a differential equation. As you all know, a differential equation is which involves an independent variable as well as a dependent variable. And coming to the actual practical terms, these equations were becoming partial differential equations in which there will be more number of independent variables that are varying with respect to a single or a multivariable analysis. That means each and every physical phenomena involving a fluid flow is governed by a partial differential equation. Now, how to solve this partial differential equation? There are analytical methods. There are the next aspect, that is numerical methods, and there is experiment. always experiment holds the greatest importance, because what we see is what we believe. So something that is happening right before our naked eye, we can believe that in without any doubt. However, generation of experiments for analyzing fluid phenomena is what we can say as a very difficult as well as cumbersome process. In that condition, they started with the analytical methods as well as the numerical methods. So, as Einstein proves it, this is one of the famous quotes by him. That means a theory is something that nobody else believes except the person proposes, and an experiment is one thing in which everyone else believes, but not the person doing the experiment. The basic logic behind that is that you can manipulate experiments. That is one of the basic fundamental problem about experiments. So suppose you are setting a certain amount of initial condition onto that experiment, you'll be getting that output based on that only. And that experiment will fail in a generalized condition. Coming to theory also, the reverse also holds true. So in that condition, looking into every physical phenomena, we move on to the analysis that is based on computational fluid dynamics. So this is one of the famous comparison charts available in the basic fundamental textbooks of computational fluid dynamics by John D. Anderson. So if it is an experimental way, we can state that it will be having a capacity of being more realistic, and however, there is problems with respect to measuring, however, problems with respect to equipments and high operating costs. That is one of the fundamental problems with respect to all the experiments, not the simple experiments that we carried out in our undergraduate level or in a postgraduate level. And telling you about the actual experiments, we will be discussing about the actual experiments, what happens in later stage. Right now, remember, whenever you need best example is, let's say, testing of an aeroplane. You can't generate models of an aeroplane each and every time and flight over there to test how the flight will behave. That is one of the fundamental problems with respect to experiment. Then you have the analytical ways in which you get an exact solution for the phenomena by solving the exact differential equation. However, when the differential equation available to us moves from the condition of linearity, what we can observe is that the solution won't be actual always. In that condition, we move on to the third aspect, that is numerical methods of solution. In numerical methods of solution, what we do is that from the analytical form, we discretize the equation into an algebraic equation, such that it is basically like we provide some assumptions. Whatever problems we do in actual engineering practice, we go for the numerical method itself. Based on a certain set of assumption, we reduce the partial differential equation available to us into small algebraic equation. So always the problem with one of the most versatile problems with the numerical method is that there will be always the association of error. Whatever experiment you carry out numerically, will be having a certain set of error, and computational fluid dynamics is one form of that numerical method. So in computational fluid dynamics, we basically employ numerical method to arrive at a result for a certain flow problem where a fluid flow is involved. So CFD is nothing but it is a tool, basically a numerical tool for solving partial differential equation. And for solving these partial differential equations, we apply three basic principles. First one is mass is conserved. That means whatever be the mass of fluid, whether that be air, water, blood, whatever be the fluid that is coming inside the system, we assume that it is conserved. For that, we have the fundamental definition of continuity equation that is we have studied starting from our 10th and 12th classes itself. Then you have the Newton's second law. That Newton's second law introduces us to a basic equation in fluid dynamics, that is the Navier-Stokes equation. Navier-Stokes equation, what it says is that the momentum is conserved. That is the basic principle behind that. Second law also states like that only. As I have stated in the slide regarding the Newton's second law, you can't have a general relationship with respect to the always. In that condition, we go for partial differential equation, and such a partial differential equation is this Navier-Stokes equation. And you have the third equation, that is energy is conserved. So for balancing of energy to the fluid flow, we have the principle that is termed as Bernoulli's equation or the Bernoulli's principle. And based on this Bernoulli's principle, we move on to the next aspect of how the system will behave. So that's all about the first two, or what CFD is, the introduction to that. Now we move on to the next area, that is the second one, how CFD is done. So coming to any computational method or any computer aided engineering method, CAE, it basically consists of these three aspects itself. First one is the preprocessor, second one is the solver, and the last one is the post processor. So these three aspects basically constitutes the basic methodology in CFD. We will be explaining all these three in detail, and not with respect to the mathematical equation again, I promise, because whatever feedback I get from my presentations is that you are using a lot of mathematical equations. So here I have reduced the mathematical equation to only one set of equation, and you will see that equation only one time. And we'll be explaining that a little bit, and we'll be much concentrating on the third aspect, that is how we can employ the CFD. So coming into the preprocessor, we develop in the preprocessor stage. What happens is that we are trying to develop whatever fluid flow phenomena you are having into a computational model. So for a computational model to be modeled inside, you first need a domain, or what we can say as an area where you can actually constitute the investigation. Suppose this being a closed area, and suppose there is water inside this system, and I need to identify, if I am introducing a fan into this and I am stirring it, I need to identify what will be the motion of the water molecule inside this. So in order to have an analytical system like this, this is my domain, and whatever the fluid and the stirrer being the force, the object that causes the force. So that constitutes the computational domain. And whatever computational domain I have to divide that into very finer species so that I will get a accurate result. Then I will explain what grid generation is basically. Then we need to identify what is the proper chemical as well as physical phenomena available to me. And I need to define what all are the fluid properties from that condition. And I need to define what all are the boundary conditions. If all these physical phenomena is completed, that actually constitutes the preprocessor part in fluid dynamics or computational fluid dynamics. The second aspect is solver. In solver, what we do is that we designate what all are the governing equations for governing the fluid flow. So the basic governing equation is Navier-Stokes itself. There is no change in that. But owing to whatever be the physical phenomena we are having, we change the governing equations. The next aspect is discretization. Discretization basically means converting the partial differential equation into algebraic equation so that we can solve that in a much finer way. And you arrive at a solution that constitutes the solver part. And the last one, that is the post processor, in which you will be having, you can interpret the results in various kinds of way. And most of you have seen how a CFD itself will look like. We'll be looking into that. So this is basically a flow domains. Suppose I want to assume this to be a rectangular room, and I have placed an object over here, and air coming inside from this area, and I need to identify how the air will create an effect on the object I have placed inside the room. I can create a domain like this. So whenever I'm creating a domain, there has to be certain conditions that has to be kept in mind. The first one is that there need to be a separate, or there need to be a specific length for that the flow to be in a fully developed manner. There has to be sufficient height for the object to generate the effect that is generated, and there has to be sufficient length to the backside so that the generated effect can be properly visualized. This is the case for almost all flow phenomena. Whenever a flow creates an effect over there, you need to actually create a domain constituting all these aspects. And you also have the freedom to set whether the domain be a 3D one or a two-dimensional one. A three-dimensional domain actually will provide a very high results compared to that of two-dimensional one. But the problem with the three-dimensional one is that it always constitutes a large amount of computational time, even though the state is much accurate, as it constitutes large amount of computational time. Sometimes we prefer for 2D. Also 2D has much more advantages, but it is not much realistic compared to 3D. So here we have a 2D domain also. Here what the 2D domain is, this is the exact cross-section of this 3D domain I have shown. It actually shows the two-dimensional aspect, and I need to study how the air that is coming inside from here will impinge and create an effect over here. So this domain I can use for studying the effect of, let's say, wind effect on a building. The same domain I can use for studying the effect of how a restricted flow passage causes a change in the flow of water. All these can be done with the help of either these three or either these two domains. So I can just need to change the fluid property as well as the what type of fluid entering. I can get accurate results accordingly. Now, I believe you have understood what basically the concept of domain is. Now, the next aspect, that is grid generation. As I have shown you in the previous first slide, first our objective is we need to generate a grid. First our objective is to generate a domain, and we'll be converting that domain into what it is termed as a grid. Over here, basically we have a grid over here. Suppose this being a computational domain, and I am finally dividing this computational domain into what it is termed as a computational grid. That is basically dividing a large area into minute areas. If you take a photograph you have taken in your mobile phone, and if you are zooming in into a large quantity, you can actually see minute amount of pixels being present. That pixel itself is your computational grid. That actually constitutes in a very minor manner the larger picture. So once I am dividing the larger computational domain into final grids, what I actually observe is the fundamental unit, that is the cell, and wherever the grid lines are intersecting, that is basically defined as a node, and the center of the cell, that is the point where the actual geometric center of the cell that is placed. You have an edge, that is basically the boundary of a face, and you have a face that is actually the boundary of a cell, and you have zones. Zones are actually divided into fluid zones as well as wall boundary zones. Then a group of these zones actually constitutes the domain boundary. Now, what is the advantage of generating a grid? So basically, what we do is that we convert the partial differential equation into algebraic equations. So whenever you are having a grid, these equations are solved over the grid in such a way that you arrive at instantaneous results, and you go for obtaining the results in an iterative manner. So you have studied numerical methods in Renjikota method and all. You have seen such iterations being happening. So whatever the iterations are happening, how accurate your solution will be, that will depend on the type of grid that is generated. So that is basically about the, I'm not much concentrating over here as our objective is basically on the application. Just now, what for a computational flow dynamic analysis, what we are concentrating mainly are, first we generate a domain, then we divide the domain into final spaces that are grids. Now, coming into division of grids, whether being a two-dimensional domain or a three-dimensional domain, you can actually choose between any of these shapes available. If it is a two-dimensional domain, we can go for a trigonal grid or a quadrilateral grid. These are the basic two aspects we have. If it is a three-dimensional domain, we can go for a tetrahedral or a pyramid, or having a quadrilateral base, a triangular face, whatever face, or we can go for any arbitrary polyhedrons that occupies the space. There are both advantages as well as disadvantages for each of this type of grids as well as domains. Now, over here, you have a type of grid generated that is a structured grid.
Hello.
So you have basically a computational domain. No problem. So in computational domain, if I can possibly divide into equal number of, let's say, geometric parts available, that is defined as a structured grid. Over here, it actually shows a physical domain in which a pipe flow with an internal entry happening. And if I can divide this into very fine areas like this, I can go for indexing that in three-dimensional space as I, j, k. That means I can properly identify where the cell is with respect to the domain I am having. And obviously, one of the most fundamental rule in CFD is that whatever domain you are having, that domain must be included in the grids, or grids must be included in the domain that you have created. You can't solve a physical phenomena without the help of grids being generated. But the basic problem with this structure type of grid is that whenever there is a complex geometry available to us, that means almost all engineering problems constituting of complex geometries itself. So whenever you are having a complex geometry, you can't go for this structural grid. I will show you the example. This is an example for an unstructured grid. Over here we have a dinosaur. So how you can't divide the entire geometry divided based on that into a finite structured one. That will be much more huge computational time, as well as it is nearly an impossible task. It is possible people have done very equivalent amount of geometries or equivalent amount of grid generation in very complex geometries, but when it comes to the actual physical understanding or the actual physical importance of that process, it will be much difficult in that case. So in that condition, we go for what it is termed as unstructured grid. However, unstructured doesn't mean that you can generate the phenomena or you can generate the grid in any law that is governing. You can generate in an arbitrary manner, but there has to be some principles or some amount of cautions that has to be exerted when it comes to generation of unstructured. When you move into what is the grid quality, there are basically three terms. First one is skewness, second one is smoothness, and the third one is aspect ratio. Also, the first three are the basic fundamentals. So in which we will be having hexahedral mesh will be giving the higher number of results when it comes to any other one, because more number of points will be there. As more number of points, we will be able to solve that in more number of points, and you can be able to tackle that process over there. And also there has to be a finite amount of mesh density. Those three are the basic fundamentals aspect. However, the quality is measured with respect to these three. That is, first one is skewness, second one is smoothness, and the last one is aspect ratio. Coming to skewness, what skewness is? If I am dividing the grid into a finite area like this, skewness actually defines the optimal cell size. That means if I am having an area like this and if I am generating an optimal cell in that divided by the cell size, that's the actual cell I have generated, divided by the optimal area. That actually defines the term skewness is all about. So this is basically applied to whenever there is triangles or tetrahedral meshes are generated. And when it comes to rectangular or quadrilateral elements, skewness is defined as the angle of the quadrilateral. So whenever we are going for having finite or very equal important computational fluid dynamic analysis, the value of skewness has to be somewhat kept between certain areas. We will discuss about how the skewness is kept in a later state. So understand there is a term skewness that actually defines if there is an actual one, what divided by, if there is a smaller one, what about that. Then comes the mesh quality, that is the change in size. Over here, you can actually observe, first I am having a trigonal element moving to another triangular element. That means the variation in size over here is very smooth. But when it comes to here, first I am having a very small area. Moving on to the other one, there will be having a larger area. In that aspect, moving on from one area to another, that is not much smooth. In that condition, your mesh is not up to the certain limit or up to the quality. Next is aspect ratio. Aspect ratio is a square, that is the basic assumption for where you are having aspect ratio 1. And another one is aspect ratio means width by length. So here we will be having the width in a higher manner. That means we will be having a higher aspect ratio. Here also we will be having an aspect ratio is equal to 1, where you will be having an equilateral triangle. That means the width divided by height, that will be equal to 1. However, over here, the width will be higher. At the same time, the length will be lower. That means it will be having a higher aspect ratio. So again, aspect ratio also applied to various certain phenomena for capturing of the phenomena, and how that capturing will help, we'll see in the application area. Now, coming into how we will choose a grid design based on the type of flow you are employing. Here, you can actually observe the velocity profile that you can see whenever there is a flow with respect to a constant object that is placed, or we can say a wall. So near to the wall, the velocity will be 0. As moving gradually away from the wall, you will be having an increasing velocity profile. Similarly, you can observe the boundary layer phenomena also. It will be also moving in somewhat a similar profile. So if I need to catch how this velocity varies, if I am placing a structured grid like this grid can't capture this change of phenomena or change of velocity, because whatever be the change happening over here, that will be happening in this area. That means this variation in velocity won't be effectively captured by the grid provided over here. However, if I am going for an unstructured arrangement in such a way that I keep the first grid line very closer to the boundary where the velocity tends to appear, I can effectively capture the phenomena in a much manner way. Similarly, moving on to this grid or this computational domain, if the flow starts from here and there are no objectives or no obstruction placed throughout the domain, and if the flow is moving in such a way that once it enters the domain, there is going to be much amount of losses or much amount of changes associated with respect to this. And these changes that are happening over here has to be captured in a much effective manner. In that condition, the grids that are generated at the entry side has to be much smaller compared to the areas where you will be having a not much variation. So the application of these two type of changes we will be looking in the application aspect. Just right now, remember, whenever there is a flow entry phenomena, or whenever there is a flow beginning phenomena, or whenever the domain consisting of, let's say, a change of area or any other object like that, in that condition, we go for what it is termed as the x-axis. Now, the smooth change of size, there will be ideally the maximum grid spacing that has to be less than 20%, and the sudden change in sinks that has to be avoided. So this is the basic example to show how these two aspects vary. So over here, this is the grid generated for a shell or a bullet that is passing through plain air, and the grid that is generated over here, you can observe that very fine grids are generated in such a way that where the shock wave that is being generated can easily be captured. Over here also, you can see that the grid is very finely made, and over here you can actually observe that the grid is very wide, and you can see over here the effect generated is much less. At the same time, since the grid is very fine over here, you can actually observe the result that is generated over here to be in an accurate manner. This actually shows the contours of pressure. So that is basically about the importance of grid. So whenever a physical phenomena is happening, where the effect is anticipated, we create a very finer mesh or a very finer grid, and where the effect is normal, we create a normal grid. The advantage is that you can actually reduce the amount of computational time when you are employing a fluid dynamics behavior. Suppose if I create a fine grid size like this throughout my mesh or this area also, what happens is that whatever system I am employing, it will be unnecessarily computing whatever values over here where there is not much effect is generated over here. So I am investing much amount of computational time in areas where the computation need to be low. Also, since if I am placing these 5 coarse grids over here, this shock phenomena that is being generated or this sudden change in pressure won't be captured. That means my result won't be that much accurate. So this is the two faces of the coin that you are facing. Coming into grid independent systems, still we are in how CFD is being done. First we looked into what a computational domain is, how a domain is created. Next we look into how a grid is generated. So whatever grid we have generated, that has to be independent of the grid size. The result that we obtain from that has to be independent of the grid size, that is, or the number of grids that we have generated. That is the fundamental law governing the computational fluid dynamics. That means that if I am having a very finer grid, and if I am having much more finer grid, the result doesn't change, I can go for the first aspect itself. So in that condition, what we do is that we solve the same problem with the help of multi-dimensional grids. I will show you an example. Over here, it consists of a rectangular domain, and inside the rectangular domain, we have a circular object being placed, and flow enters the domain and impinges upon the cylinder that is being placed over here. And this is the classical problem of flow over cylinder in computational fluid dynamics. So the change of effect of pressure as well as the effect of whatever fluid flow happens wherever the areas that the flow impinges upon this cylinder. So I have created very fine mesh around the cylinder, and since the effect is not much significant over here, I have created an open mesh over here, and I am plotting the coefficient of lift. Coefficient of lift basically means that the force that which causes the object to lift or move up, that is defined as the coefficient of lift. So for this arrangement, I am getting a variation in lift with respect to the cycle time in an oscillating manner. Moving to my second grid, what I did is that I made the grid over here in much more coarser compared to this. Over here, the mesh generated is much more simpler meshes. That means the coefficient of lift generated over here, instead of this oscillation, it tends to come over near in a linear manner. Now I increase the number of grids again, going for much finer meshes near to the cylinder that is being generated, and I go for again running the simulation or running the calculation. Again observe that there is linear phenomena only and there is not much variation. But the difference between these two grids is that over here, that is the third grid that is generated, the computational time actually employed will be much more higher. But while here, I'll be getting the same result as that of the third step in that of the second case itself. That means I need not invest much more computational time while employing the mesh 3. I can go for the mesh 1 itself or mesh 2 itself. I will be going for not going for mesh 1, because if I am employing mesh 1 for the solution, I will be having a variation in coefficient of lift compared to that of the second one. But going from 2 to 3, the variation has linearized or it is becoming a constant one. In that condition, I can fix the number of elements of the mesh as the mesh 2 itself. So this means that whatever grid that you have generated for a fluid flow, that has to be independent of the type of grid that is employed. So that is the most impressive as well as the most important aspect of grid independency as well as computational fluid dynamics. So I believe you are able to grasp the point. Now the only equation I'm going to solve this here is the Navier-Stokes equation. First, you have seen what a domain is, what a grid is, and what grid independency is. So once I have generated a grid independency, I need to apply the governing equation that I'm going to apply on this. This actually shows the Navier-Stokes equation in 3-dimensional unsteady condition. So in Navier-Stokes equation, you basically have the dependent variables as pressure, variable temperature, as well as density. Velocity, you will be having velocity in x, y, and z direction, u, v, w. And coming to the independent variables as x, y, z, and t, that is the position as well as time. So the independent variables x, y, z, and t, and the dependent variables pressure, velocity, temperature, and density. You have stress and all, again function of that aspect only. So with respect to this dependent variables, with respect to the independent variables, how these aspects will vary, whether being any fluid flow associated with respect to that, we need to solve for that fluid flow problem. Suppose you will be having a domain, and into that domain I have generated this corresponding one equation, and now I need to apply this equation onto that. So before applying the governing equation onto that, I need to talk on a simple aspect in fluid dynamics. Not in the name it's simple, but in actual practice, this is the most complex aspect, that is turbulence. This is one of the famous quotes by Heisenberg, who invented the Heisenberg's uncertainty principle. It is believed that he said this in his deathbed. He wanted to ask God about two things. First one is relativity, second one is turbulence. And he is definitely sure that the God will have an answer for the first one, that is relativity. So what turbulence is? This, I think again, most of you can recognize. This is the famous painting of Leonardo da Vinci. In one presentation, I used to say, in my first classes in CFD presentation, I mistakenly pronounced Leonardo DiCaprio. That happened 2 times. So this time I have written it correctly over here, Leonardo da Vinci. So da Vinci painted this fluid flow starting from an orifice, and once it hits, you can actually observe that over here, it will be having a basic normal condition. And once it starts settle down, you can actually observe changes in that fluid flow. That variation in the flow pattern, we call that as turbulence. Turbulence is always around us. If you are standing in our room and if we switch on the fan, the air moves in a swirl manner, that is another effect of turbulence. If you are making your morning coffee, if you are making your morning tea, and you are swirling that with the help of a spoon, that is turbulence. over here, you basically have a vortex that is correspondingly being generated from a airplane wing. It is actually termed as the wingtip vortex, and they have colored a dye to actually show the actual phenomena of turbulences. So this turbulence actually plays a significant role in our equation, because whatever equation we have over here can't actually account for this turbulence, because the fundamental governing principle of turbulence still it is unknown, and the exact solution for this Navier-Stokes equation, that is also unknown, because you can't apply whatever equations you are having. Let's take F is equal to ma. You can apply that to a moving truck, the collision of a moving truck. But what is the impact of that truck on the air around that? You can't predict that with the help of a Navier-Stokes equation, because according to conditions, this equation will vary, and there are no exact solution for this Navier-Stokes equation, as well as there is no exact solution for turbulence. These two are one of the most important conditions, or one of the most important physical phenomena, and these two, and the solution for these two is actually resolved as the Millennium Prize for problems in mathematics. That means there are so many unsolved problems in physics, and if you are able to solve that with the help of an exact solution, you will get $10 million as your prize. These two are the contenders for those two conditions. These two are the contenders for one of the Millennium Prizes, one of the most phenomenal problems, unsolved problems in physics. So the basic fundamental phenomena associated with turbulence, this is again not defined in the physical we are having, equation we are having. This equation also doesn't account for turbulence. We'll be going for some other equation when we need to go for account for turbulence. So prediction of turbulence, as I've said, it is much more difficult. So when you have to account for any fluid flow, turbulence has to be accounted in that, and actual models for turbulence available to us is very much limited, and the usage of that much models is also very much limited. Now, coming to the picture I have shown in my first presentation, the Vincent van Gogh's Starry Night. So Van Gogh has actually depicted this picture to show the effect of luminance of light, how light travels, how light behaves in particular way. He painted that as one of this, and this is considered to be one of his masterpieces. So what he has depicted over here is an eddy, or a turbulent flow that is being generated. Over here, you can see a very large eddy that is tending to die out, and this large eddy supplies the energy to the smaller eddy so that it again constitutes into a larger eddy. So it's not my explanation. Andrei Kolmogorov, one of the famous Russian mathematicians, he actually observed this phenomena. Not this picture, he observed turbulence phenomena, and he developed the equation in such a way that the turbulent fluid length, or how much is the length of turbulent, that is actually proportional to, the generation of turbulent fluid length, that is actually proportional to R is to 5/3. And that turbulent generation you can actually observe in stars, you can actually observe in starting from your coffee cup. When you are moving in a scooter, again, the turbulent phenomena with respect to the same mathematical model will be applied. And scientists have observed the same variation mathematical progression in this picture also. That means Van Gogh has incorporated that mathematical phenomena into his painting. He was unaware of turbulence. What he did was that he is considered to be one of the most impressionist painters. That means they will be making the use of the light pulse flicking and all that thing, and he made that into his painting. Only in the later stage, in 1990s, only they have identified the mathematics behind this picture, and that actually represents turbulence is all about. That means there will be generation of large eddies, and those large eddies will transfer energy to smaller eddies, and you can see that smaller eddies are generating, and this cycle will continue. And there is a fun fact about this painting. He developed or painted this painting when he was admitted in an asylum after he cut off his own ears.
Sorry to disturb. Like your voice is breaking. Maybe that might be like.
Hello.
Sir, your voice is breaking. Your voice is breaking. Then I'm there. Like
clear now?
Your voice is breaking. Yeah, it's clear now, and we are streaming on YouTube live as well.
Okay. So you can actually observe a larger eddy supplying the energy to a smaller one, and continuously the eddies are continuously being generated. So I believe this actually summarizes what the phenomena is. We were talking about Van Gogh, yeah. And he painted this when he was admitted in an asylum after he cut out his ears. That means his mind was considered, and he himself admitted to that asylum. That is one of the most fun fact in that. Leaving all that aside, this is all turbulence is also all about. That means generation of eddies compared to the actual phenomena behind that. We assume that to be the turbulent intensity or turbulent velocity, but that all apply only for certain aspect of. Moving on to our presentation, that is discretization. So first we generated a domain. From the domain, we generated a grid. From grid, we did what? Grid independency. That means we made the flow domain. Moving on from the number of grids that is generated, then we identified what governing equations we can apply for solving a problem. Now you can't exactly solve that partial differential equation, as you have seen the number of independent variables on that. There are more number of dependent variables, and there are only independent variables to be 4 only. So in that condition, we can state that we need to equations into algebraic equation. That area or that aspect, we call it as the discretization. This discretization itself can be considered to be a very large area. So what I'm doing is I'm giving you only a fundamental understanding. So there are many discretization schemes available to us. Even there are actual discretization schemes with respect to analytical method in which we can employ Gauss elimination method or LU decomposition. But however, when it comes to engineering phenomena or whenever it comes to simulation of fluid flow, that is not much important to have an exact solution like by employing LU decomposition or Gauss elimination. We'll be going only for an approximate solution. There will be some amount of error, as I have listed out. There will be errors in the form of discretization. So what our objective is to minimize the error. So there are two fundamental phenomena or two fundamental processes, two fundamental techniques we employ when it comes to discretization. First one is the finite element discretization. Second one is finite volume discretization. So in finite element discretization, what we do is that we apply the equations or convert the equations in an area where we apply it onto grid points over here. When it comes to finite volume method, we apply the equations or convert the equations into what it is termed as the cell centers over here. So most of the computational fluid dynamics analysis will be using the finite volume method. That means you will be dividing the cells and you will be calculating the equation that you are having in the partial differential form into algebraic form and applying that equation onto the cell centers, where you will be having conditions nearer to any one of the cells will be known, and with respect to that known condition, and that known condition, what we do is that we assume the initial flow field. We assume that this is the initial condition and we solve the equation based on that. We solve the equations based on this equations itself, on the cell centers itself, so that you get an accurate flow field of the analysis. Now, I think I have touched upon what CFD is and how CFD is done. That means I have not done an entire justification to what the actual applications or what the actual phenomena is. I have given you only a brief introduction or a very simpler understanding of what all things are happening. And as our orientation is towards this, I'll be explaining or I'll be concentrating much more on this aspect. So where all CFD is used or applications of CFD in research as well as industry. So coming into the advantages of using CFD, first one is this is relatively inexpensive and comparatively fast than that of the any other techniques available to us. And it provides a complete information about whatever investigating phenomena, whatever phenomena we are investigating in with respect to. And it is much more easier to carry out a parametric study with the help of CFD analysis so that you can design the aspect in much more similar manner. There are no similarity constraints. We will see what similarity and what are the constraints we'll be facing when it comes to an actual phenomena. And you can have more number of experiments in CFD compared to that of any other, any other analytical or experimental method, and you can account for any of the failures you are having. And when it comes to the major disadvantages, there is a major concern for the accuracy as well as the reliability, and there will be results will be affected much more by the parameters, and you always need to validate the results that you generate with the help of CFD. These all are the fundamental advantages and disadvantages. I know most of this might be confusing to you, but I believe we will look back into this slide once the presentation tends to a conclusion, and you will be able to have a much more understanding of how this can be done with the help once we finalize the presentation. Moving on, this graph I have taken from a review paper. So these are the base, finally telling this is the basic applications where you can employ CFD, starting from aerospace, moving on to environmental application, you can employ it for predicting the pollution and what the climatic conditions are, meteorological calculations. Coming into physiological applications, you will be having how the cardiovascular flows are generated and how this, we will look into these aspects in a detailed manner. This is just for an introduction, how this can be applied. And now apply of this. So all these processes you can apply either in a manual way by coding all these equations, all this generation, or generating the model with the help of simple codes. This is considered to be, this was a primitive form of computational fluid dynamics. People used to write long, lengthy codes with the help.
Sir, your audio is not audible. Bobby sir, like your voice is unstable, like you have some audio issues.
Sir? So there is nothing appearing. Your screen has stopped.
Sir, is the meeting over?
So we had a technical glitch at the end. Sorry. At the same time, Zoom and Asian and broadband have crashed. It's a problem from host side. Really sorry for this this technical issue. You know, this is the one big problem with when we use technical virtual platforms. Really sorry for what happened so far, and thank you for staying back. We'll continue the session. Bobin, sir. Bobin, sir.
Yeah. I'm here.
Thank you, sir. I'm really sorry. We had some technical issue.
No issues.
Zoom and Asian and broadband have crashed. That's the problem that we are. Currently, we are running on a backup internet facility.
Okay.
We can restart. Thank you very much.
Okay. Can someone tell me where this actually dropped? I continued a little bit. Where were we? Actually,
we were discussing about applications, sir.
we're discussing about applications. Okay. We'll start from
industry applications.
Okay. We'll start from here. Okay.
So mainly the slide showing the softwares. I think your audio lost it. That slide.
Okay. Thank you, Ravish. Thanks a lot. Okay, so when it comes to the tools that we get available with us for this computational fluid dynamics, we basically have the first one is the most primarily used one, that is codes. So we hardly use codes now, but there are people who are adamantly using codes. Codes are nothing but whatever we have seen equations, we write that in basically with the help of programming languages like C or Fortran. And with the help of that codes, we run the facility or we test the equations in the flow field and we solve for the entire equations that is available with us. That is one of the fundamental aspect available with us. Then comes commercial solvers, in which you don't need to code anything. Just like what we do in Windows, we just need to type a document. We just need to open Microsoft Word. So in Ansys Proven, what we do is that we just click on the file that we need to operate. And by that file, we'll be able to
Bob, sir?
Yes.
Yeah, now we can hear. Now we can, sir. Please go ahead, sir.
Now, with Ansys Proven, we basically have a commercial solver developed by Ansys such that whatever conditions we need, we just need to click on that, and with respect to that condition, that flow problem will be solved. Then you have another solvers like OpenForm. Again, OpenForm also works with the principles of coding itself. It is an open source software, which actually means form, field operations, and manipulations. Then you have Phoenix, that is again another code. Then you have Star CD, SimScale. SimScale is the most advantageous code right now because they have an online facility, just like this Zoom app we are using. So we just need to load in what are the conditions we have. We will get the solution from the web browser itself. That is one of the fundamental advantages of SimScale. So these are all the various options available to us. These all are the various options available to us when it comes to the commercial solvers as well as open solvers available. So the first application, that is the fundamental aspect, that is aerospace. This is considered to be one of the most traditional area of computational fluid dynamics, because the entire development of computational fluid dynamics we can attribute to this aspect, that is the aerospace engineering. So when it comes to aerospace applications, there are two types of flows that we can associate with respect to aerospace. First one is external flow. The next one is internal flow. External flow is the one in which where you will be having external flow is the one where you impinge the flow onto the aerodynamic structure or the flight body, and with respect to that flow, how you can model the various physical aspect on that. That is the external flow. Then you have the second type of flow, that is the internal flow, that goes inside the engine or the propelling device, and see how the propulsion aspect is being done. So the application of CFD primarily comes in these two aspects. First one, design stage. Second one, validation stage.
Sir?
Yes?
Bobin sir, in between, your audio is it's something like unstable, or your break-in voice, something. Is there something, some issue with your microphone or something you're using?
Am I audible now? Or is it breaking?
You're audible now, but as the session progresses, we are losing your audio.
Okay.
But the participants can hear.
Participants can hear?
Yeah. No
Okay,
problem.
then great, sir. Thank you, sir. Thank
Okay.
you so much, sir.
Oh, thank you, Ram. Thank you, boss. Okay. Now, when it comes to validation of the design, the design, as you know, is primarily being done with the help of certain softwares. And with respect to that software, if one design is finalized, you can't directly go for manufacturing that design when it comes to an aerospace industry, because as you know, the cost will be included for manufacturing of that will be very much higher. In that aspect, what we do is that we carry out numerical experiments, as I have said, with the help of CFD. We generate a computational domain, and with the help of test that is already being done, we carry out the numerical analysis and we see whether those two tests are exactly matching with respect to the previous case. That means you will be plotting the coefficient of lift, that is the amount of lift force generated for an object, and you will be plotting the drag coefficient, that is the opposing force acting upon that object. And this is one of the ways. There are many other ways. So once that design is finalized, you can apply that onto varying geometries so that you can actually generate very higher amount of result with respect to that. So this is an excerpt from the design development team of Boeing. So here you can actually observe a fully developed or a fully designed stealth fighter aeroplane, which employed with all the missiles and all the other aspects with respect to that. You can't fly out an actual model every time. So you generate a model. As you can see, coming to the domain, this actually shows the external domain far away from the area only. They have created a very fine mesh to the faraway places. And when it comes to the nearer area or nearer to the surface, you can see that the grid is so much small that whatever be the flow that is coming over here creates the effect, and that can be observed. Attachments. These attachments actually act as what it is. That is, I'm currently working on. That is an ISRO Respond project. Respond means sponsored research under Professor Dr. K. Muralidharan Nair of our institute. I am the co-principal investigator of that. Oh.
Sir, there is some discontinuity.
Okay.
Bobin, sir?
It's not audible now.
Yes, yes, yes. Bobin, sir, there is some discontinuity in audio. Could you just check? Audience, participants, please bear with us for some time. Like sir is checking his audio. We'll resume shortly, very shortly. Bobin, sir, am I audible to you? Bobin, sir. So participants, could you hear something? Like, could you just respond to the chat box? Do we have any audio issues?
Rahul sir, your voice is audible.
Okay. So we have a problem with maybe let's check. He has some audio issues. In the meantime, please bear with me. I will share you the feedback link as well. See, currently I have off this. Currently, this form won't accept any responses, but however, I can send you this. This is the feedback link of today's program. Now you could not you won't be able to type any responses because currently it has been not though currently it won't accept any messages. So I have shared the feedback link. You could fill the feedback link once the session is over. So currently we are facing some audio issues. We'll be receiving it very shortly. Sir, please, can you mute your audios?
The chat box is not working.
Sorry?
I didn't get the link.
See, in chat box, I have shared the feedback link. You could complete. See, someone is using this audio. Please, can you some mute, please? Thank you for muting it. So I'm waiting for Bobin, sir.
Sorry, I got disconnected somehow.
Yes, sir.
Oh.
Sir, you just joined, sir.
Yeah.
Yeah, sir. You can go ahead with your screen sharing, sir.
Yeah.
Thank you, sir. Thank you.
Disconnected somehow.
No issues, sir. No issues. We'll go.
We're discussing here, right? Is the screen sharing enabled? Are you guys can see this?
Yes.
Yes, sir. Yes, sir. Yes.
Okay. Yeah, we were discussing mainly about the wing generation or the amount of pressure that we applied on a wing. So whenever you are having a fully developed flow over aircraft wing, the basic model of turbulence that we apply is K omega or K epsilon, considering at what velocity the flight is going to fly, as well as the Mach number of the flow, so that the flow can be whether being considered to be a compressible flow or incompressible flow according to the flight. And according to the model that we have in flow, we can again go for what it is termed as the large eddy simulations or the direct numerical simulation we have. And basically we have two types of flow, that is the internal flow as well as external flow. What I have discussed right now is the external flow. Moving on to the internal flow available, that is the propelling device we basically have. A propelling device mainly consisting of various arrangement, like here, the example that we are presenting over here is a turbofan arrangement in which you have a compressor, you have a combustor, and you have a turbine coupled together. And the air that is being sucked inside, whether being in an compressible range or an incompressible range, onto that, the fuel is being added and the combustion phenomena takes place. And the major advantage with respect to doing a simulation like this is that you don't need to actually look into the safety aspect we are going for in an actual experiment. In an actual experiment, if I am running an engine and I am increasing the amount of airflow into that, there is a high chance of explosion. As I have stated in the previous slide. When it comes to an actual engine like this, when you are going for a computational fluid dynamics simulation, in the first figure A, you can actually observe that there is a void region that is shown in the center as the blue area that actually shows the negative pressure contour that is being developed, even though when there is an impingement of flow into that, then shows the propagation of flame propagation that is shown in figure B, and it shows how that as combustion progresses, how that excess air is being circulated. So I can vary this, I can keep on doing this experiment by varying the certain conditions with respect to that and varying the parameters also with respect to that. And when it comes to actual simulation experiments and all, what we can actually observe is that if I am employing that into be in the aerospace region, I can get less reduced cycle time. Cycle time actually, as you all know, that is the time that we can observe by creating an actual design into a practical one. So reducing the cycle time, that actually means increasing the cash flow for an industry. And similarly, we can actually observe the reduced risk associated with respect to that. That is one of the fundamental aspect with respect to application of aerospace into application of CFD into aerospace. That, as I have stated, this is one of the classical or traditional area where CFD is widely being used. Next is astrophysics. As again, man have always been thought of going into the outer space, and computational fluid dynamics has helped a lot of that. The first figure onto the left side, it actually shows two stars that are merging together to form another star. So this is one of the most common phenomena that we can see in solar systems. So what they have simulated over here with the help of astrophysical fluid dynamics equations. They are otherwise termed as the EMG equations, Estes material-Godseck equation. It is just a relativistic version of the Navier-Stokes equation. That means you apply the relativity principle of Albert Einstein into phenomena, and they have developed the variation of density according to that. The second equation, actually, it shows a spanning that is happening in different scales of space and time. So that term may be much, jargonistic as it sounds, but that is actually what it is meant by time travel. As you can see that if you cross over from one position to another position, in the left-hand side of this black figure, you can actually observe a minute variation happening in first, and after a long time, what happens is you will be having a large variation. That is the entropy associated with respect to the system. So in EMG equations, what you account for is basically the entropy. As you can reduce this entropy, you can actually jump out from one space to one time zone to another time zone. That we have seen all in the interstellar film. That is one practical application of this. This research is being carried out by the University of Chicago. Another important aspect of astrophysics is the actual prediction phenomena of other planets, including our own. Onto the left hand of the presentation, you have a actual representation of the planet Jupiter, which is photograph is taken with the help of the Hubble telescope. And to the right hand side, you have a GIF image of the computational fluid dynamics simulation of the same astrophysics phenomena that is developed by NASA. The importance of Jupiter is that Jupiter is having the highest gravitational pull for any planet that it can account for. So such gravitational pull will reduce the effect of that. And over here, you can actually see that the layers are the atmospheric is moving in layers that actually account for a particular phenomena that is defined as the Kelvin-Helmholtz instability. This instability we have already seen in recent times. I hope you already have seen the Dalgona coffee, in which there are two shear continuous fluid flowing across, and because of that shear difference between the fluids, you will be having a velocity difference. Next classical application is again one of the fundamental aspects, that is automobiles. In automobiles, you have external flow as well as internal flow. Coming to the left-hand side, you have an aerodynamic design of a car in which the car is held stationary and flow moving over there. That means the external aerodynamics is fixed. Coming to the next aspect, that is the internal fluid flow, that is the swirling motion of how the system or air will be coming inside. Again, the third aspect is combustion. First, external aerodynamics, coming internal flow, and third aspect is combustion. But right now I have not included any presentation about combustion in my presentation. It is mainly because combustion itself is a wide phenomena. And coming to computational fluid dynamics of combustion, there are varying aspects such as the concentration of the objective, the concentration of the mixture, what type of mixing happens, what is the flame types, what is the chemical kinetics. So all these constitutes a very large area of research. So in that condition, we are currently not looking into the combustion aspect. We are looking only into the internal fluid. So this actually shows a graphical representation of the external aerodynamics in which a single plane of air is being passed over the designed car. The simulation is being done with the help of OpenFOAM software. You can actually see that how the flow attaches the car and how it detaches. Next comes the thermal cabinet as well as the cabin comfort. So coming into the heat that is coming inside a system, here the energy equation comes into picture a large ways. In the other two conditions, we'll be mainly concentrating only on the type of flow that was employed in the system. that is mainly for aerodynamics aspect. And coming into internal aspect also, energy was not considered because we will be looking into what type of swirl was created inside. Coming into the thermal load management, as the energy equation comes into picture, the effect of energy equation can be modeled with the help, more realistically with the help of K omega model rather than any other, along with shear stress transport model. This I have not explained. This K omega, K epsilon, all this actually deals with what type of, how you are modeling the turbulence. Just remember that wherever I am using K omega or K epsilon, K means turbulence intensity and the other is turbulent viscosity. They are just looking into the areas where you can model. Next is biomedical application. This is one of the thrust areas that is happening right now, as biomedicine constitutes a much more area, and blood, as you all know, it is a Newtonian fluid, non-Newtonian fluid, sorry, my mistake. So blood execute a what important phenomena that is termed as shear thinning. That means if the blood is much more agitated, it becomes less viscous. However, the blood viscosity, you can observe that it is not dependent on time. What matters is the amount of stress. Onto the left-hand side, you can actually observe a computational domain model of an actual human heart and how flow that is happening inside the system. Then you have the second aspect, that is the trunchial module where that is being generated. And this type of computational fluid modeling actually helps a lot of patients that is need to be done, that is in need of surgery. Because of surgery, as you can observe that the patient may have to go through many painful tests for identifying what the actual problem is, if there is any issues with respect to his nasal cavity. But here, instead of going through that test, with the help of the mere scan itself, they can model as well as identify
and simulated in
sorry, as they can identify what the issue is. Next is one of the most novel areas in research happening in our country. That is the brain computation division that is being happened in IASC Bangalore. They have a development system itself over here. That is, I have started that, the brain computation division. And that division is started by IASC Bangalore along with Chris Gopalakrishnan, who was the chairman of Infosys. And they have trying to develop a complete exact replica of human brain, so that can be developed and that can be seen what happens inside the system. So here, what it shows is that a combination of MRI along with tractography, along with computational fluid dynamics. They have accounted for the turbulence also, but there is currently no validating result that this is correct or not. As we have seen in aerospace, the first application, there will be existing tests with respect to that, and that solver will be applied onto that so that that result is correctly validated. But when it comes to biomedical application, especially this development of brain or now, there is no such mathematical model, there is no such experimental model available for the human brain or how the system works. Only we are having is analytical models. There is no experimental work. So in order to do experiments, we need to cut out a person and take out his brain. Dead people's brain won't do work. So that is one of the fundamental limitations over here. And the color graph that actually shows over here is that how neurons are propagated. The blue colors actually shows how it goes up, and in green, what it shows is that how the nerves or how the synapses are traveling, whether in the forward direction as well as in the backward direction. Next, I'm going to show a small video where the impinging COVID crisis is how effectively managed with the help of computational fluid dynamics.
and simulated and compared. In this digital simulation, there are two people who are positioned 0.5 meters apart, and one is wearing the protection while the other is sneezing. You can view the trajectory of the various particles emitted during sneezing and where the particles are deposited. With these simulations, the facial protection or mask design can be improved to further protect the person. These scientific simulations are conducted in our Simulia software, which enables dynamic simulation or fluid or airflow, as is done very commonly.
This is one of the presentations made by Dassault System. They are the pioneers in this computer-aided engineering. You know, Dassault System. It is the systems that are supplying the Rafale aircraft to India. So what this simulation shows is how social distancing can be effective. That is one aspect, and how effective the development of mask can be. So in the first half, you can see that when a person sneezes, how the particle is traveling across that. So when here only there is no viruses are included in the module in the presentation, there is only what they have shown is only the corresponding water droplets or the sneeze module itself, and how the last aspect they have shown how a proper mask can save you from the effect. Next aspect is buildings. Designing of buildings, that is one of the crucial aspects when it comes to the smart city projects and all. You can see that how a wind profile is generated, and when that wind impinges on the object, how it gets stagnated flow, how recirculation happens, and all these are technical terms. Just try to remember that when it impinges on a building, there will be some effect on that. And the actual stream that is generated, it gets separated into mainly 16 number of flows, and all these flows generate some amount of impact on the building. And this actually shows a turbulent model that is being applied. And one of the fundamental problem with the buildings is that, suppose a building is arranged like this, and we will be having a converging flow. We assume that the system to be in a convergent flow, obeying the convergent flow principles, but that is not true always. It is an open flow only. It is not a closed channel flow. So when it comes to actual building design, this actually shows the top view, how wind will be traveling across a building. And since it is observed that a converging section, it is expected to have a very high pressure as well as velocity. But in actual practice, you can actually observe that the diverging flow is happening. That is mainly because of the open flow in buildings. Also, there also we make use of turbulence. Turbulence can be modeled again with the help of certain aspects available to us. And coming into actual building development of cities also, we can go for modeling in such practice. Next aspect is chemical industries. And when it comes to chemical industries, as well as areas where there are multi-fluid flow that is being employed, CFD plays a major picture. The first picture shows a magnetohydrodynamic in which both a molecular level simulation is happening, and the second one shows a tank onto which steam is being dispersed. That means there is two-phase flow. In one phase, you will be having it getting cooled into water, and in another one, you will be having it getting generated into steam itself. So if there is a change in such physical phase is happening, we incorporate one more model into our simulation. That is basically the volume of fluid method, especially in we employ that phenomena, especially when it comes to the other area, the ANSYS fluent module. So whenever you are having a volume of fluent approach, it actually means that half of the portion will be empty or filled with liquid, and the other half will be filled with air or any other phase that it is being present. Next aspect is electronics. So as we are going through the informational age, we all know that the size of the system is coming down. At the same time, the computational power is increasing. So where to place the system effectively so that effective coolant can happen, and where the system can behave onto its way, that we can design with the help of any computational fluid simulation software we have. This is one of the thrust areas which again I am working on. This actually shows an experimental setup with an actual model, and the results that actually shows are two different solvers are being employed to generate the result. One is OpenFOAM, that is the open source software. The other is the ANSYS Fluent. And onto the left-hand side, you can actually see the experimental setup. That means we have validated the model that we have generated This was an internal funded project from my institute itself. And we were able to generate 2 standard publications out of this. So here, what we have actually done is that we have developed a solver in such a way that how the flow pattern can be seen with respect to an electronic device. Here, the model is an heater itself. Now, this is the next aspect of that work, where we have actually simulated that into an actual, that solver that we have developed into an actual model that shows how heat dissipation can actually happen. Again, here also energy equation plays a major picture compared to the fluid dynamic aspect. Next aspect is nuclear technology. When it comes to nuclear technology, as we all know that we are moving into another renewable areas of energy generation as the pollution is going on. Nuclear technology or nuclear area is one of the thrust area. And you can see that Europe is one of the most sophisticated countries that develop the nuclear technology compared to other, because they have an optimized technology with a very reduced cost of production. Just like we say that we can see tea shops in around our corner. There is a saying in France that they can see nuclear reactors in every corner. So when it comes to actual nuclear reactor operation, computational fluid dynamics plays a thrust area or a major role when it comes to the safety of operation. You can't directly operate a nuclear reactor always, so that the system can be studied accordingly. So in that condition, we generate a nuclear reactor model with respect to the operating conditions. That means the void fraction, operating parameters and all. And the system, the results over here actually shows how you can vary the type of arrangements of nuclear reactor inside. And basically, you will be having a fluid system that employed to carry out the heat, that is the coolant system, and with respect to that coolant system employed. Now, this is again another project that I have worked. This on the left-hand side, it actually shows the advanced heavy water reactor. That is the research reactor being developed by the Indian Pioneer Research and Research, Baba Atomic Research Center. I was there for 1 year as project training. And I was able to study on a thermosiphon system. A thermosiphon is nothing but, instead of having a a force system to remove the heat, you use the density difference of the fluid itself to carry out the heat. So there will be the size of the reactor. It comes around, let's say, 1,000 to 1,500 meters. That is approximately 1.5 kilometer. But coming into the inside of the core, you place minute devices which is having external cross-section like this, that can take up the heat and they can reject the heat, and they will be in very high number. So whenever there is very high numbers of such devices are there, you can take up the heat. Again, turbulence comes into picture. So fluid dynamics equation along with energy equation comes into playing over there. Coming into another aspect, that is sports. So when it comes to sports, again, the major aspect is racing sports itself. So you can actually see the major problem with sports is that coming to aerodynamics design, you can actually employ the system to be in a still manner and flow in a normal manner. But when it comes to sports, the system has to move. That is one of the major disadvantages when it comes to conventional CFD with respect to sports CFD. So there are actually shows an F1 car as well as a normal racer, and you can actually observe how the pressure is being generated and how streamlined flow will help to reduce the pressure. Again, turbulence is going to play a major role, and this is one of the most simulated experiment right now, how an object can be moving. At the same time, there is a movement of mesh. There has to be a movement of the object. So this is a simulation result from the McLaren Sports Academy. Now, please watch this video.
That is very good. The swing works, the Oracle again. Quite brilliant from Simon Jones.
What a great piece of reverse swing.
He got 6 for 53 in the first innings, and he did it with reverse swing, getting it to go both ways. This one has come back sharply, well outside off stump there, but not there. That's some piece of bowling, I can tell you. It's 263 for 6.
That was one of the defining moments in the 2005 Ashes. Michael Clarke was going on in a very stealth manner, and he got dismissed by a clear piece of clever bowling, that is reverse swing. As you can see that the ball was pitching very outside the off stump, and Clarke judged it will be going out to be a normal outswinger or an in-swinger. There is no chance that he's going to take out. He takes his guard off leg so that there is no chance for LBW. But what happened over there is that is the reverse swing. So this is one of the thrust areas happening in ICC right now. BCCI has employed lots of computational fluid dynamics experts to identify how the ball can employ in reverse swing direction. So when it comes to conventional swing mainly depends on how you place the swing of the ball and how you keep the rough edges as well as the smooth edges. So when the ball is moving in the normal area, it will tend to swing towards the rough edges, as you can see in conventional swing. But as the ball progresses, as the match progresses by 30 or 40, let's say overs, what happens is that the ball, both sides of the ball becomes rough only. In the initial side, you will be having one side rough and one side smooth in the natural way. There is the problem of ball tampering is there. I agree with that. We are not discussing about ball tampering now. So as the time progresses, you can see there will be the objective of reverse swing. So what basically happens is that there won't be, so what causes the swing is the difference between the laminar as well as the turbulent flow. That means the flow will change from laminar condition to that of the turbulent one. But when it comes to reverse swing, what happens is that the separation points that can be very lateral compared to that of a normal flow, and there will be turbulent flow on both sides of the flow. Coming to conventional swing, there will be only one side that is rough. That means that rough side will be having turbulent flow, and the variation in separation point can be employed so that this figure also shows like that. That means there will be vorticity generated on both sides of the flow, but when it comes to an actual reverse swing ball, there won't be much of that. So how computational fluid dynamics helps over here is that it will help you identify what will be the actual separation point to be employed when it comes to, and this can help the batsman also, and this can be helpful the bowler also. How the batsman helps is that he can identify if the bowler is going to hold the ball at a particular point, it is going to be an reverse swing ball. And similarly, if the batsman is not so clever, the bowler can employ that technique and he can generate the reverse swing and he can get out the batsman just like how Clarke got out. The next aspect, that is turbo machinery. Turbo machinery, as you know, turbo machinery constitutes of one of the major area in fluid dynamics as well as fluid mechanics. Turbo machines are of many types. There is pumps, turbines, and all these help to improve the performance of our industry. And by employing computational fluid dynamics, you don't need to construct an arrangement like placing whether in a radial curved vein or in a backward curved vein, and how the volumetric flow rate can be measured. Similarly, how the pressure variation can affect the increase in flow. Again, turbulence will come into the picture as well as swirl will come into the picture. We have to model for that. We have to model that with the help of commercial solvers, especially SimScale. This is one of the most widely used solvers when it comes to turbo machinery now. So I hope you got an idea about what the advantages and what the disadvantages are right now. Similarly, when it comes to other areas like providing a complete information for all and other aspects, we can actually observe how the system will behave and how the system will change according to the input constraint given. So I hope this answers your query of how numerical experiments can be performed. And moving on to the last aspect, I just need to add one more point. Right now, what computational fluid dynamics, how it is developing is that they are currently being employed to generate what it is termed as machine learning algorithms, so that whatever result you have, that can be combined, and so that new results can be generated with respect to that. I had one more slide onto that, but as I changed my system, that was not added into this system. I'm really sorry for that. So machine learning algorithms can generate much more advantageous system than the conventional system, so that artificial intelligence can predict how the flow will be, and artificial intelligence can tell you how the system is going to behave when you change certain aspect. So that's all for today's presentation. Thank you for holding with me, and I'm really sorry for the in-between technical difficulties faced from my end.
Not
Thank you for the presentation.
Not maybe thank you so much, sir. No, there is absolutely, I should apologize for it, because this is the first time we are facing a lot of technical issues today. Actually, we are simultaneously hosting 2 to 3 programs today, but the problem with the Airtel, Asian and broadband. So that's why we have a technical glitches in between. And thank you, sir, because for adjusting with this all technical glitches, and you are adapting to changes. We are apologies to you, and thank you very much, George, sir.
And I really thank all the participants. I really thank all the participants, especially participants from my host institute or Baselious College. I can see a lot. I can see my colleagues over there and my students over there. I'm really thankful for your support, and all other participants. Thank you. Thank you for your patient listening of me. I know this is not much. What do you say? Didn't give you much insight into the problem, or as well as the computation fluid dynamics. But as you know, it's a wide area. So I just give you snippets of that. And for whatever doubts, I have written my mail ID over there in my presentation. So you can reach back to me for any doubts regarding to that. And once again, thank you, Rahul sir, for inviting me to this lecture. And I thank all the participants for their patient listening. Thank you.
Sir, actually, I have given you the host permission. Can you just turn it back to me, sir? Can you just give re-host me? I have given you the host permission. You are the host now. Can you just give the permission to me now?
Yeah, 1 minute.
You can. Yes, sir. Yes. Participants, please stay back for your questions. Yeah, thank you, sir. Yeah, I am the host now. Participants, you can stay back, sir. Actually, thank you to all dear participants almost attending in this webinar who are in Zoom, as well as for maybe 15 to 20 people who are watching in YouTube live as well. Thank you. I'm stopping the YouTube live stream now. So participants, if you have any particular question, those who are watching in the YouTube live stream, you can write directly to Bobin sir. So the participants in Zoom now.